Hello, I'm Supraja, and together with Andren, today we will present our new attack WeSee on AMD SEV SNP. So to get started, let's look at a quick overview of our attack. We attack AMD SEV SNP, which is the latest and most secure generation of AMD processors. We mount our attacks on an AMD SEV SNP VM that is managed by the cloud service provider's hypervisor. Crucially, for our attack, the hypervisor is responsible for interrupt management of the VM, which means that the hypervisor can inject interrupts into the VM at any point during its operation. Typically, when the OS in the VM gets an interrupt, it executes a handler. For WeSee, we use this observation that the hypervisor can arbitrarily inject interrupts to trigger handlers in the guest VM. These handlers leak or change global state in the VM, compromising its confidentiality and execution integrity. We build strong attack primitives and demonstrate them on VMs that execute Linux and OAK operating systems. Now, before we can look at any more details about our attack, we need some background. So let's begin by looking at how an AMD VM communicates with the hypervisor if it needs help executing some instruction. In our example here, the VM first sets up some state in the RAX register that the hypervisor will need to process the request. Then it executes the instruction. When the VM executes such an instruction, the hardware generates an exit to the hypervisor. The hypervisor directly accesses the VM state and reads the RX value. Now the hypervisor can perform its operations to fulfill the VM's request and then write back the results to the VM. In this case, it writes back the value of RAX again and then resumes VM execution. Now, if we switch gears to AMD SEV SNP, where the hypervisor is untrusted, consider a VM that is executing an instruction that needs hypervisor support. But now, because the hypervisor is not trusted, SEV SNP locks down the VM state and the hypervisor cannot access it anymore. To help the VM execute this instruction, however, the hypervisor still needs value to the data in RAX. An obvious solution is to use a shared buffer between the VM and the hypervisor. But how do we decide what to write in this shared buffer? AMD solves this question by introducing a new VMM communication interrupt, or WeSee interrupt for short. With SEV, when the VM executes an instruction that needs hypervisor support, the hardware triggers a WeSee interrupt to the VM. This allows the VM to decide what data to copy to the shared buffer in the WeSee interrupt handler. For this, however, the handler still needs to know what type of instruction caused the WeSee interrupt. So the hardware also sets an exit reason register with the information that the handler needs. In our example, the WeSee handler looks up the exit reason register, decides to copy the value of RAX into the shared buffer, and then exits the hypervisor. The hypervisor, as before, can read this value from the shared buffer, operate on it, and write it back. Then when the VM resumes execution, the WeSee handler again selectively copies values from the shared buffer into the VM state. Again, in our example, it copies the value back into the RAX register. This mechanism essentially ensures that the app does not need to be changed to execute in the AMD SEV SNP VM with the right kernel support. Now, all of this looks fine, and it seems to work. The question is, what could go wrong? Well, as we will find out soon, quite a lot. Turns out with SEV SNP, the hypervisor can arbitrarily inject this WeSee interrupt at any point during the VM's execution. See that the VM in this case is not executing any instruction that needs hypervisor support. The hypervisor can interrupt this VM at any point. If that sounds bad, well, it gets worse. The hypervisor can also control the exit reason register when it injects the interrupt. So it can influence the state that is being copied in and out of the VM by the WeSee handler. Now you might ask, how does this impact the security of the VM? Consider this example where the application has stored some secret value in RAX. If the hypervisor injects the WeSee with the right exit reason at this point, as we saw earlier, the WeSee handler will copy the RAX value into the shared buffer. This is bad. The hypervisor can now read the secret value, compromising the confidentiality of the SCVS and PVM. But the hypervisor can do something worse. It can also change this value. And the WeSee handler will copy this back into the application. So the hypervisor could potentially also compromise the execution integrity of the VM. By now, I hope I have convinced you that by arbitrarily injecting WeSee interrupts, the hypervisor can compromise the VM. So next, to demonstrate powerful attacks, we build expressive primitives using different exit reasons. Let's take an example where the hypervisor sets the exit reason to VMM call. In the WeSee handler for VMM call, it copies out the RAX in the shared buffer and then copies the value back from RAX into the VM state. So what we saw before is the effect of the hypervisor setting the exit reason to VMM call. This essentially lets the hypervisor read and write the value of RAX arbitrarily during the SEV SNP VM's computation. Using this, we build two attack primitives to read and write to the RAX register. Now, there are a total of 16 exit reasons that are possible. For WeSee, we use two others apart from VMM call, specifically MMIO write and MMIO read. Using these, we build attack primitives that can read and write to kernel memory. Additionally, we also build a primitive that can skip instructions. That is, it increments the instruction pointer. This is particularly useful to avoid some undesirable side effects that the handler might have that might lead to its crashing and our attack not being successful. Next, I will hand over to Andren, who will talk about our write kernel memory primitive in detail and discuss the case studies that we build and potential mitigations for WeSee.
So thank you, Supraja. Next, we want to demonstrate the inner workings of our kernel memory write primitive that we built for WeSee. But first, let's walk through a benign case where an SNP VM does an MMIO read operation. So consider the following MMIO read instruction. We have a load of memory from RDI register into RBX. Now, when executed within an SNP VM, the hardware triggers a WeSee exception indicating that an MMIO read operation is happening. The WeSee handler is called. Now consider this simplified implementation of the WeSee handler. The first thing the handler does is that it calls this function getPointer to receive a function pointer pointing into the application context of the interrupted application. Now, in this example, this pointer points to the RBX register, since this is the destination register of the MMIO read instruction. Next, the WeSee handler exits to the hypervisor, and the hypervisor supplies the MMIO read value. This value is then being written in the dereference pointer, which updates the application context of the interrupted application. Now, when the WeSee handler resumes the application, the MMIO read operation is completed. So now, after we understood the benign case of an MMIO read operation, let's dive into how we abuse this particular handler for arbitrary kernel memory writes. So in order to mount our attack, we need two ingredients. We need to hijack a pointer, and then we need to dereference that pointer and supply it with a value we want to write. So as a first step, we as the attacker inject a WeSee exception indicating that an MMIO read operation is happening. As already shown in the benign case, the first thing the WeSee handler does is that it calls this getPointer function to receive a pointer to the application context. Now, according to x86 calling conventions, function return values are always stored in the RAX register. So we can use this insight and use our write RAX primitive to overwrite this function return value and hence overwriting pointer. Now, this pointer points to memory of our choosing within the SNP VM, which is the first ingredient of our attack. There are now several checks that will otherwise crash the handler. So we have to use a series of our write RAX and skip instruction primitive to recover this corrupt state. Next, the WeSee handler exits to the hypervisor, and we as the attacker supply it with a value for the MMIO read. Since we control the value, and this value is then being written into this dereference pointer, which we also control, we have both primitives for our arbitrary write. To write 8 bytes of kernel memory, we require a total of 34 WeSee interrupt injections. And this attack primitive works with accuracy of 100%. In our paper, we demonstrate the WeSee attack with 3 different case studies. First, we leak kernel TLS session keys using our read memory primitives. This requires us to inject WeSees 288 times. We further demonstrate WeSee with a case study where we disable IP firewall rules. This requires us to craft a shellcode, which then replaces the filter function that's used in IP tables. This modified shellcode or this modified filter function then always returns true, hence not filtering any package. This requires us to inject 238 WeSee interrupts. And last but not least, we build a case study to obtain a root shell where we inject over 2,800 interrupts. Now we have a video prepared for this third root case study. And before I play the video, just for your information, on the left side, you see the log of the SNP VM, and on the right side, you see the hypervisor log. So let's play the video. The first thing the VM does is that it boots. So during boot, we use a series of our read, skip, and write primitives to defeat physical and virtual kernel ASLR. After the VM has booted, and after having defeated that, we inject a shellcode to spawn a root shell. Now, this shellcode lies on a code path that is triggered when the VM is being pinged. So after we inject this shellcode, we actually ping the VM, which executes the shellcode, and then we can open up a reverse shell to obtain root privileges in the SNP VM. We responsively disclosed the WeSee attack to AMD, and they released a hotfix for the mainline kernel. This hotfix is already merged in version 6.9 and is being tracked under the CV shown here. Now, to demonstrate the mitigation, let's walk through an example. We, as the attacker, inject a malicious WeSee interrupt indicating a VMM call, even though the SNP VM does not actually execute a VMM call instruction. So the WeSee handler is being called, and now before it starts to leak internal states, this new patch set is executed. What the patch set does is that it compares the opcode, so the instruction, and checks whether it matches the exit reason. Since in our example, the SNP VM does not execute a VMM call instruction, this fails, and the kernel simply panics. Only by checking the opcode, it's not clear if this is actually a regular move or a MMIO move. So a more sophisticated patch would then also have to consider the operands, which are currently not checked in the patch set, and then potentially do a page table walk to ensure that the operands are in fact within memory mapped regions. This is just one corner case. In the paper, we discuss other corner cases as well. So as you can see, this patch set quickly can become complex, which is why it's only a hotfix, and which is why we also advocate for hardware-based solutions. And in fact, AMD already has one in the works. But before we present hardware-based mitigations, let us quickly recap on VMPL privilege levels in SNP. So SNP VMs have, similar to rings on x86, different privilege levels. VMPL 0 being the most privileged and VMPL 3 the least privileged. Now, one potential deployment for these privilege levels is having a trusted bridge running in VMPL 0 and then your Linux kernel running in VMPL 1, 2, 3. Now, this bridge acts as an interface between the untrust hypervisor and the Linux kernel and can selectively decide if it wants to route interrupts through, so basically filter interrupts. Now, this is motivated by lift and shift because the Linux guest can continue to use its legacy interrupt interfaces, and the bridge can introduce a new interface to talk to the hypervisor. Now, AMD introduces 2 modes called alternate and restricted mode for interrupt injections. And these modes, together with a new interrupt vector, so-called doorbell interrupt, can mitigate the WeSee attack. So let me walk through the different injection modes to explain how these modes can mitigate WeSee. Having no defense enabled, the hypervisor, as we have seen in this presentation, is able to inject any interrupt into the SNP VM. With alternate and restricted modes, the hypervisor can no longer inject into VMPL 1, 2, 3. It's only able to inject into VMPL 0, which is the trusted bridge, which then, when implemented correctly, can route this interrupt to VMPL 1, 2, 3, hence to the Linux kernel. The hypervisor is not able to inject any other interrupts, hence the WeSee attack is no longer possible. As of now, no software support is merged upstream into the Linux kernel, so we were unable to test these modes against WeSee. Besides this, we also analyze other hardware-based mitigations for WeSee, so please check out our paper for more details. WeSee is part of a new class of attacks we call Ahoy attacks. Ahoy attacks use malicious notifications to break trusted execution environments. In this presentation, we introduce WeSee. You can also check out our Usenix security paper that we call Heckler. Heckler uses different interrupt vectors to break Intel TDX and SNP. Our proof of concept exploits are available at ahoyattacks.github.io. Thank you.